chemical formulas and chemical nomenclature, one of the first things we need to do is be sure we understand how the compounds and substances are classified. So when we talk about chemical formulas, we're certainly talking about the elements and molecules. And we know compounds and so forth like that. Elements have their own symbology, if you're well aware. The ones that I want to emphasize to you at this point are the non-descriptive nomenclature for elements. Ag, argentinium is where it comes from. Na for sodium, it's naturium, is where it comes from. Pb for lead, it comes from plumbum. So, those kind of things are the ones that kind of slip away from the young scientists here. And so, please go through, look on the back panel of your textbook, or bring them up on Google. But try to isolate those that have weird symbols compared to the names and what they are. And so, so you will be able to pick those out on test day. One that I like to give is manganese, okay, and magnesium. These are two different substances, okay, so check mark that. Little stuff like that, the nomenclature of elements in themselves that you need to pay close attention to. Okay, manganese is a transition. Magnesium is group 2. So, they have different chemical physical properties. Well, they'll show up on a question on your exam, and that'll cause problems because you could select the wrong one and it leads you certainly to the wrong answers. Now, in molecules, we find there are really two primary classifications, ionic and molecular, and then compounds. In the ionic compounds, you can see there at the top of the handout, they always consist of a metal and a nonmetal. Now, a nonmetal can be, of course, one of the elements on to group 4, 5, 6, and 7. However, there are also things like polyions, and the polyion collection that have negative oxidation states are classified as the nonmetal collection. And from there, we break this down into binaries, binary compounds, binary molecules. Now, a binary ionic compound is one that has two different elements in it. Now, it may have more than 2 atoms. I want to note this. CPDS compounds. Binary is 2 different elements. Okay. Aluminum bromide. Okay. And sodium chloride. Both of these are binary. Two different elements. But of course, the aluminum bromide, of course, has 4 elements in itself, 4 atoms making up that structure. Okay. Then you have the polyatomics, which is a metal plus a polyion. And that context, as you see down at the bottom right of that block of classifications, metal and a polyion, and we'll talk about the other notations that are in there right now in a second. At any rate, are based upon the 2 parts, a metal and nonmetal, where the nonmetal is, of course, the polyion also. So if we wanted to write an ionic compound or identify an ionic compound, we need to go to the periodic table, and certainly we need to know that where the metals are here, as well as the nonmetals. And I've given everyone a collection of polyions, and working with this. So we'll try to write a few compounds. So we take something from group 1, sodium, and we add that to, say, a chlorine. I'll put sodium up here as a plus. And chloride. If chlorine is neutral, it's called chlorine. If the Cl has an oxidation state negative, it's called a chloride, IDEN. So these go together in a one-to-one like this. Now, bear with me for a second. If I go to calcium, we see that it's in group 2. And we learned last time that anything in group 2 is a fixed charge plus 2. Let's put that with chloride. Well, we find out when we write its formula, it's calcium, and we have to use 2 chloride. Well, where does that come from? Well, that comes from a fundamental rule about putting these elements together. It's a natural rule. And it's sum of all charges, or oxidation states, must equal 0 in writing these ionic compounds, unless it's a polyion and it has a net charge. We'll get to that. Anyway, when you look at the charges on these, that's why we have to have 2 chlorides, because you have to have 2 negative charges to cancel out the 2 positive charges here. And so that's a common denominator for all ionic compounds. The sum of all charges must be, or oxidation states, must be equal to 0. And that includes those with multiple oxidation states. We can take manganese. It carries a +2 charge. Well, I can put it together with sulfur like that. It's a 2- charge. Well, if I put it together, I could write this manganese and sulfur like that. But one rule, another rule, in addition to the first one I just gave you up here, is that if you have subscripts that can be reduced to smaller whole number ratios, then do so. Okay? That's the common practice in writing ionic compounds. And that's not true for molecular compounds when we get down there. C2H4 has to be left in C2H4, not CH2, is the point. Because it identifies a specific substance with chemical physical properties. But here, there's not going to be a collection of manganese sulfides. So the procedure is reduce to smallest whole number ratio. So the corrected formula, MNS, is the proper formula for writing these. And so that's true. If you can reduce it to the smaller number, whole number ratio of elements in the compound, then do so. Okay? In this, we take the polyion as a particle that's carrying a charge. Now, each element in there has what we call a formal charge. But collectively, we look at a polyion as having an overall charge, or a net charge. So in writing an ionic compound that contains a polyion, it'd be the metal plus the polyion, and structured so that it would, sum of charges equals 0. So when we talk about the most common polyions in our little course, and if they get complicated, I'll explain those too. But you have NO2s and NO3s. Nitrate is an NO3 -1, and this is a nitrite. Now there are rules for identifying the ITE ending versus the ATE endings in structures, and it's based upon the oxidation states of nitrogens and oxygens and so forth like that. But that's really at this point in your game not needed. So if you'll learn these as given and memorize them, then it'll save us a lot of time later on. But you go through here, and here there are only 2 positives in here, This is the ammonium ion, and this has two names really, mercurous or mercury 1. Please, parenthesis 1 goes in the parenthesis down there. It means that there are two mercury 1s. It takes mercury by itself carries a plus 1. So you hook them up, you got 2 plus 1s. So it comes out plus 2. So long story short, that's the best I can do with that. At any rate, everything else in there is negative. You go in here, this is a sulfite. And where's the sulfate? Yeah, right here, SO4. And this is a chromate. And this is the dichromate, Cr2O7. This is 2 minus. You know, you go all the way, and you just got to learn it for, using them in compound. Hydroxides use a lot. So phosphate, PO4, 3 minus. And thiosulfate, S2O3, 2 minus. So you need to go down through here, ClO. Here's an interesting set. The perchlorate, ClO4, cyanide, CN. That's what we call a non-oxo anion. Everything else has an oxygen in it except that cyanide. Hypochlorite, ClO minus, and bicarbonate, CO3. Bicarbonate by itself is a CO3, 2 minus, like that. And so when you hang a hydrogen on it, like that, it cancels out one of these and becomes a minus 1. So remember that. ClO3 is a chlorate and permanganate. Now this one has a minus 1 charge. Don't get in there with a minus 2 or anything else. Here's your carbonate. This is an acetate. Acetate, you'll see C2, C3H, if I can get my head straight, 2 minus. It's also, and used in acids. If you put an H out here, it becomes acetic acid. And you'll see an HOAC like that, or you'll see it written H3CCOOH. But, you'll see these things show up like that. And all these parts in here are acetates. And the big long formula, that's an acetate. Here is a C2O4, this oxalate. Remember this, 2, 4, 6, 8, this is oxalate. Got it? Okay. That makes it easy to remember. 2, 4, 6, 8, this is oxalate. You don't put a 6, 8 on there, though. Anyway, let's see what else is in there. I think I got them all in there. Anyway, how do you use them? That's the issue. So you pick a metal from the left side of the chart, say sodium. And what I think carries a plus 1 charge. It's one of those fixed charges. And we pick NO3. Well, you have to know it's a minus 1 overall. So this is a particle. It has a structure, and we'll learn how to deal with structure later on. But you put them together in a NO3. Well, this is a plus 1, and this is a minus 1, and if you add those together, you get 0. So that is the correct ratio for that compound. Calcium plus 2, and the C2H3O2, the acetate. It only has a minus 1. So if I put those together, calcium and C2H3O2, like that, and recognize this is a plus 2 and that one's a minus 1. Plus 2 minus 1 is not 0. So you have to put that in parentheses and put a 2 here to indicate that calcium acetate contains 2 acetate ions. Now, you have to use the parentheses or you'd wind up with 22 oxygens in there. So that's the simplest explanation for the parentheses I can give you. Now, of course, you have again the reduced to smallest whole number ratio, calcium sulfate. Well, this is a plus 2 and this is a minus 2. So this would honestly be reduced to calcium sulfate. And this is the appropriate formula for putting that together. Again, reduce if it can be reduced, reduces to the smallest whole number ratio. Now you have what we call. Let me say this before I do give you this next this calcium. give you this next note. Ionic compounds are salts. So there's synonymous names. They're the same. So if I'm talking about a salt, I'm talking about an ionic compound. If I'm talking about an ionic compound, I'm talking about a salt. So you'll find out the importance of this later on in the course. But when discussing these, please keep those kind of equal to each other and as you go through the course. So some salts have an affinity or attraction for water, and they are called salt hydrates. So what you can have in a salt hydrate is, say, barium chloride, like that. No, it's beryllium. I'm sorry. Let me take that back. It's beryllium chloride. And it will attract two water molecules. And this is what we refer to as a hydrate, salt hydrate, or just simply a hydrate. And its nomenclature, and we'll get to this in more details, beryllium chloride dihydrate. And of course the dihydrate, I can write that a little more clearly, I think. There we go, dihydrate. I guess you can read that. But of course the di in there indicates di. There's in contrast, we can show you this, CuSO4.5H2O. That's a hydrate of copper sulfate, and that's called copper sulfate pentahydrate. Actually, it's copper 2, and I'll explain that as we get back into the chart. Copper 2 sulfate pentahydrate. Now, the dot means you're adding on 5 water molecules. It doesn't mean multiply, because when we start, some of you know about formula weights. And so if you were calculating the formula weight of copper sulfate pentahydrate, you would add 5 water weights to the anhydrous form. Anhydrous, I better put that down too. That's a hydrate with the water as a hydrate. Anhydrous or anhydrate, no water. No water attached. So like that. So we've covered ionic compounds, binary ionics, polyatomics in their context, okay, and plus thrown in a hydrate. Now, how do you name these things and putting them together? Well, there are two kinds of ionic binaries. One where the metal is a fixed charge, and two where the metal is a variable charge. And last lecture we talked about, well, here are the fixed charge, group 1, group 2, group 7, and then I blocked out some triangle elements for your group, plus 1, 2, 3s, and from tantalum back, 5, 4, 3, 2. When I say, okay, you need to know where the fixed charge is. Well, how does that help you with the variable charges? Well, if it ain't a fixed charge, it's a variable charge. And there are two ways to tell what the charge is. One from the name or from the formula. All right, we'll see how this works. Okay, let's work with the fixed charge 2 words. Okay. So, again, if you need the fixed charge, remember group 1, group 2 are plus 1 and plus 2 respectively. And then you have a minus 1 over here. All right? So, finding silver, that's a plus 1. Here's a plus 2. And these are plus 3s. And over here, find tantalum, plus 5. Then go backwards, plus 4, plus 3, plus 2. We already know that. Plus 1. So plus 5, then plus 4, and plus 3s, all the way up and down, plus 2s and 1s, like that. All the others in here, all the other metals in here have variable charge, like copper. Copper has a plus 1 oxidation state and a plus 2 oxidation state. If we want to distinguish between the two, say copper chloride and copper chloride, I must do one thing here that's very important so you can distinguish between the two, and that's put the oxidation state in parentheses and Roman numerals in parentheses after the metal, like that. So this tells you that you're using a copper 1, and of course chloride is a fixed charge, it's group 7. And so this would, of course, lead to one-to-one combination between those two, right? Plus 1 plus a minus 1 is 0. So that conforms to the sum of charges equals 0 issue. And then, but copper 2 says you're using an oxidation state of plus 2 to combine with minus, and in that case, you'd have to have 2 chlorides to get a copper L2. Now, that's one way to tell, is from the nomenclature, I have to put the oxidation state back to the metal. If it has a fixed charge, you don't need to put anything now. Okay, like tantalum chloride, or TaCl5. You don't have to put anything. So in that context, because you know when you look on the chart, tantalum is always a plus 5, whatever it goes into it. At any rate, what if you have something like, well, we'll go back to manganese. Mn Br2, okay, like that. So what's the oxidation state on manganese in this case? Well, there's a couple of ways to tell. You can use some intuitive knowledge. You remember the bromide is always a minus 1. You got 2 of them, so this is all a minus 2 over here. So what would manganese have to be? It'd be a plus 2. So there you have, like that. Another way to deal with this is to crisscross. The 2 goes up here, and the 1 goes there. Some of you have seen that little trick before. Whatever that 2 is goes to a plus. If you put it over the metal, metals always come plus. And the bromide is, well, there's a 1 there, so it'd have to be a minus 1. That's another way to tell what it is. And another way to tell what that oxidation state is, if you have MnBr2, what does it mean in terms of sum of charges? 0. So I have manganese plus 2 bromides must equal 0. And I'm making symbols be the charge numbers. So if we don't know what manganese is, but we do know that's a minus 1, now you have a little simple algebra equation. And so you solve that, and you have a plus 2. Okay? So when you add 2 to both sides. And so you have different ways of defining these. Well, it's also true for polyions when you deal with that. Okay, so if you're working with polyions, you have a Na plus a NO3 minus. Well, you put them together as we've shown you earlier, NaNO3. Well, what does the rule say? Well, if you're working with polyatomics, over here it says there are 2 issues, and they use the same idea. If they're fixed, the metal, you don't have to put a Roman numeral out there. But if they're variable charge, you have to put that Roman numeral to identify that oxidation state. But all you have to do is name the polyion afterwards. So here is sodium, and sodium's a fixed charge, so we don't have to put a parenthesis. And NO3 is nitrate. So in essence, that's the same idea. Copper 2 sulfate. Of course, that would be Cu with a plus 2 plus a, well, I could put that up there, a plus 2 like this. And SO4, 2 minus, and appropriately we reduce the smallest whole number ratio and be copper sulfate. So when you look at this, you know this one's going to be a -2, and if you only have one of them sitting there, that's got to be a +2. So it's the same logic in terms of sum of charges equals 0. You can always trace back to that in the case of trying to identify oxidation state. So you can determine it from the formula or the name. If the name doesn't have anything in front of the metal, then it's a fixed charge, and you, in the polyion or whatever it is that you're using, will have a fixed oxidation state for that structure. Calcium +2 plus, PO4, 3 minus. I put that one together, and you have a calcium and phosphate. Goes over. Calcium and a phosphate. How about that? Okay. Well, calcium, as you know, is a +2. This is a 3 minus or -3. Okay. Now you can use the old crisscross if you want to. That 2 would mean you'd have to have 2 of those, and then you'd have to have 3 calcium. That's just another way to do it. Or you can add everything up, because you'll know what the oxidation state of calcium is. And so that would ultimately become Ca subscript 3 with a PO4 subscript 2, like that. And if you test it, you can add up all the oxidation states. They should sum to 0, is the nature of it. At any rate, such is nomenclature and the oxidation states in writing ionic compounds. You gotta know your polyions. Okay, calcium chloride. What do we know about this? Well, is calcium a fixed charge element? Sure, it's +2. And chloride's a -1. So we got a +2 hooking up with a -1. So I have calcium chloride. Well, then I'm going to have 2 chlorides. You have +2 plus 2 minus 1. And that has to equal 0. So you can do them in your head, or you can lay them out and work through them. Oxalate. Remember what I said earlier? C2O4, right. 2468. Oxalate. Okay, so I got a sodium and C2O4. There you go, for oxalate. That makes it easy. Anyway, this is a -2 and this is a +1, so you can crisscross if you want to, and this would become appropriately Na2C2O4. Okay? Okay. Hydrogen sulfide. Well, I'll save that one to next. That one is a binary acid. Potassium permanganate. How about that one? Okay. So you have to know your polyion structures. MnO4 -1, potassium +1. Add those two together, and it's KMnO4. So you would not need an additional subscript in there for that structure. Oh, how about copper phosphide? What? Now, phosphate is the name of the neutral form of phosphorus. Okay? Now, phosphorus is the neutral form name. But when you put a charge on it, then it changes to an IDE. And there's one other rule: if it's by itself on the end of the formula, it's an IDE ending. So this is by itself on the ending because you see IDE on ending. I'll show you some other examples. So this would go to copper and a phosphorus formula, okay? And so this is a -3, and this is a, it doesn't tell you, phosphide -3. You don't have a 2. Copper has, copper 2, yeah, sorry. I forgot to put the 2 in there. So it's copper 2 phosphide. So this is a +2, and so this would appropriately become copper subscript 3, phosphorus subscript 2, but it's phosphorus is by itself. Let me show you another one here. If you had magnesium oxide, that IDE ending on there, that means the oxygen is on the end of the formula, but it's by itself. It don't have anything to go with it. So it's magnesium +2 plus oxygen -2, and that would go to MgO, reduced to the smallest whole number ratio. And so oxygen's by itself. Here's one, another one. How about sodium sulfide? See, the IDE is that, okay, that's sulfur, so it means you got sodium hooking up with sulfur, such that there's only one sulfur sitting there. Oh, well, I mean, one sulfur. Sulfur's by itself on the end. There's not a polyion structure with an IDE ending like that on it. So that would go to sodium sulfur. Well, this is a +1, and sulfur is -2, so you would have to have an Na2S. You don't need anything other than that because sodium is a group 1, and it's always a +1 in that collection. Okay. How about lead dichromate? So, lead 2 dichromate in there. So lead chromate. So we're going to hook up lead +2 plus Cr2O7 2-. A lot of people like to write 2- on there instead of -2. Whatever works. Now, of course, that's added together to get 0, so we own 1 to 1. But so we don't need to put subscripts on this because it will reduce. Okay, so you got a lot of elements in there. Now, well, listen to me carefully on this. A lot of it you're starting to get a handle on. How do you, if you're given the formula like this, how do you tell what the metal is and what the polyion is? So you got 2 metals up front in this. So you may not know about the chromate or the dichromate, CrO4. And so you have to decide, well, where's the polyion? And the simple rule is, look at this, the elements from left to right. Elements from left to right, the first petition, the first element. And then everything after that petition, after the first element, is polyion. No matter what or how it's written, it'll separate like that. I got one. See the first metal, then follow everything else is the polyion. So you have zinc, and what's this? You look at the bottom of your polyion chart and it's bicarbonate. So the zinc bicarbonate is what the name of it is. Well, zinc's a fixed charge, so you don't need any parenthesis stuff. And so that makes sense to go. Here's one. Very important that you get used to this. Remember I told you there are only 2 positive polyions that you're really going to run into right now. There are many positive polyions, but for right now, There's ammonium, and then there's mercury. Well, mercury's undeniable. It's Hg. And it's the only liquid natural state, basic standard state, on the periodic table. Well, that doesn't look like an Hg at all. So when you see this, you petition this after the NH4. That's an ammonium ion. This is the only one you have to deal with. That's why I say you got to get used to this. Everything else will be a metal on that left end, except for ammonium something or another. And this is acetate, ammonium. So the name of that is ammonium acetate. First, second name, like that. So, and don't forget the hydrates in there, okay? So hopefully I've given you enough cross-section of naming and writing formulas that are going to get you started. And as we get deeper in, you get more experience with it, and they get a little more comfortable. All right. It is online. You go to your class website, M Unlimited, and it'll have practice exams and worksheets. So pull up the worksheets. This one's in there. You can go down through there and practice naming compounds. Now, some of them are molecular. I think everything. We've got some acids in here that I'll talk about right now. Now we're down here in this molecular compounds department, and you see the same idea goes through, and we find molecular compounds are binary two different elements. They can have more than two atoms, the same idea. Or you take molecular acids. These are polyions, but the metal side of that polyion structure is a hydrogen. It's what we call an acidic hydrogen. It ionizes. You put it in water. I'll say more about that. And it breaks away from the molecule. That's what we call an acid structure, like that. And the binaries, it breaks down, and we'll talk about those right now. And the acids, it breaks down into a couple of sets of rules. So we'll look at this first. And the binary molecular compounds has no hydrogens. We name two words, and this is kind of easy to understand. And then you have hydrogen with an IDE ending where it's a single element at the end of it. So molecular compounds, nomenclature. Okay, we'll start out with the binary molecular. Two words, okay? A prefix. Plus the element IDE ending, because there's going to be only one in there. Now, these prefixes are listed in the top right-hand corner up here. Yeah, as was the question earlier. Yeah, you got to learn those. Okay, so we'll be using a lot of these kind of structures. Well, they're not that difficult. Now, there's only one rule, which we're using, say, CO and CO2. The rule I'm trying to give you is if you have one element of a kind in a formula where the first element is only one of them, then you just name that element followed by the second element, IDE ending. But in the second element, you use the prefix. And I use these two compounds because you're familiar with them. This is carbon monoxide, okay, indicating one. And then you're familiar with carbon dioxide. Okay, so using that, the first element, if it's by itself or a single element, then you don't name anything after, you don't put any prefixes on it. However, if the first element does have multiples in it, N2O5. That's real. Here is a case where you do use prefix. Use a prefix for both of them. Okay, we're going to take a break for about a couple of minutes right now. So that's all right. Go ahead if you need to. I don't stop anybody. Okay, so this would be dinitrogen pentoxide. So, and that's all I want to get. We'll go ahead and take our break now. And but if it has multiples on the front end, you do have to use a prefix. If it doesn't, if it's a single issue like this, you do not use a prefix. Okay. So now we want to get into the bottom half of the methods of nomenclature and formula writing. These, we want to look at the binary hydrogen-containing molecules. And to do this, I want to draw out a kind of a little periodic table thing and show you how it comes together quickly. And I'll move it to full screen. It's just the periodic table, the non-metal side in groups 4, 5, 6, and 7, primarily in here. And we're going to assign carbon silicon -4 charge, -3 for nitrogen, phosphorus, and then oxygen, sulfur, selenium, -2, and the halogens, remember, -1. Yeah. I need to add a hydrogen onto each one of the elements listed, enough hydrogens to cancel out the negative charges that are at the kind of the top of the page. Now, when hydrogen undergoes ionization and enters into a molecular compound, it enters in as a +1. There's only one that we'll look at in the distant future that's a -1. It's hydride, but we're not concerned with that. So every hydrogen from here to the end of time, until I tell you different, is a +1. Also, oxygen is always a -2 until I tell you different. You want to give me? So I'll make that over here. Hydrogen will always be a +1, and oxygen a 2-. Now there is a case, hydrogen peroxide, for example, where hydrogen is a +1 and H2O2. But for right now, oxygen will be a -2. So if we need to cancel out the 4 negative charges, how many hydrogen would I have to have? Well, obviously 4. So I put a CH subscript 4. So that's the molecular formula for that compound. Same way with silicon. I will need 4 hydrogens. And so we'll proceed to add hydrogens to each one of the groups. Nitrogen will need 3 hydrogens. Phosphorus will also need 3. Oxygen. Now at this point, let me show you a little trick here. Hydrogen typically is listed left on the right side of the formula, but this is easy to remember too. If you put hydrogen on this one, it has to go on the left. And water, if somebody asks you what the formula for water is, you'll always say H2O. So when you get to that group 6, hydrogen goes on the left of the elements, H2S and H2Se, hydrogen sulfide. But on the group 4 and 5, hydrogen goes on the right by tradition. And same way here, HF, HCl, hydrochloric acid, HBr, and HI. So when you get to those petition between 5 and 6, you want to switch sides with the hydrogen. Just wait. Now you have 2 types of names. You have what we call a common name, and then you have a IUPAC name, which is a systematic naming of the compound. That's when you have the IDE ending in singular elements at the end of this. But of course, CH4 is called methane, and it is the simplest hydrocarbon. And there is a series called the hydrocarbon series. It's based on the prefixes, and methane, ethane, 2 carbons. Methane is one carbon, CH4. Ethane is two carbons. Ethane, propane, three carbons. Butane, four carbons. I'll show you how to do the hydrogens in a second. Propane, butane, pentanes, and this is where the prefixes start coming in. Pentane, hexane, heptane, octane, and no name, let's see, 7, 8. I'm trying to get them all on the same page. Heptane, octane, nonane, C9, and decane, C10. Well, the number of hydrogens that attach with each one of these is 2 of the carbons plus 2. Always. It's homologous series. 2, 3, 6, 7, 8, 6, 8, 10, 12, 14, 16, 18, 20, 22. So that's what is the most important series. That's the first thing. I didn't get them all on there, did I? That's the most important series you're going to learn. That's the first series you're going to learn if you go to organic. Methane, ethane, propane, butane, how many ever carbons that go. Now, that's a unique group. It's referred to as the homologous series. And it's the also known as the aliphatic hydrocarbons and saturated aliphatic hydrocarbons. And when we talk about the word saturated, it means it does not have double bonds in it or triple bonds in it. Everything is, all the bond sites for carbon are satisfied, of course, hydrogen. If you were talking about, say, propane, it would look like this. And I'm not going to, at this point, we're not talking structure. So there's no double bonds in that, so that's a saturated hydrocarbon, is what it's referred to as. And other common names are silane. I'm not going to, I think, give you a homologous series for that. Here's ammonia, and of course water. Now, the others in there have IDE endings or systematic names. Phosphorus trihydride or hydrogen phosphide. That's what we'll use. You'll notice it's a single phosphorus. And this is hydrogen sulfide. Of course, hydrogen selenide. You can look through the scribbles up, but you follow my logic. Now, I want to separate these out into 2 groups. I'll show you. There we go. There we go. Okay, just some terminology that you're going to need as we go forward in here. Most of the work that's done in this text and lecture course are in water, but occasionally a halide will show up, hydrogen halide will show up that's in the gas phase. It has implications in how much of it breaks down. You know, we'll get to that in due time. Now, if it's in water, it is a hydrogen halide. Now, halide right here is hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide. See what I'm giving you the relationship on? But when you get over here, it's in water and it becomes an acid. But if they're in water, as we're showing, this then becomes hydrofluoric. Hydro, and you get the FLURIC, you'll get used to that. Fluoric, and then you tag it with an acid. Same way with here, hydrochloric, acid, hydrobromic, acid, and hydroiodoic acid. And they all end with that IC, acid. Now, three of these fall under what we call, and you'll see this in the next chapter, the early next chapter, what we call strong acids. Just a preview. And that means they ionize 100%. You will not find any molecules of HCl, HBr, HI in the water solution if you have one. But hydrofluoric is the only weak acid in that collection. There is HF molecules floating around along with hydrogen ions, hydronium ions actually, and the fluoride ions. So just starting this off, one's in water, one's not in water, and it defines how you name that substance. Hydrogen halide or hydrohalidic acid in that context. Okay. So in looking back at our chart, you can see how these two kind of come together in that last note here. One's a hydrogen halide and one's a hydrohalide with an ic acid attached to it. And so you can see those rules. And molecular, and they come under the heading, of course, molecular acid. Now, polyions involved in molecular acids. This is H plus a polyion, an ionizable hydrogen plus a polyion. And the name of the polyion begins to become very important that you understand those and know them. And that if the polyion ending is an ATE ending, sulfate, nitrate, then you drop the ending ATE, put an ic acid on it, nitric acid, sulfuric acid. You've heard of some of those, okay? And if you have an ITE acid, ITE polyion, you drop that ITE and you go OS acid, hypochlorous acid, and I'll show you that in a minute, okay? Or nitrous acid versus nitric acid. Nitric acid is one of the strong acids, and you'll learn that next chapter. But nitrous acid is a weak acid in itself. And we'll learn about that too. I mean, that's not part of this, but trying to illustrate the difference. So when you write out a polyion plus a hydrogen, use enough hydrogen to neutralize the oxidation state on the polyion. Now, there is a collection of molecular acids identified by what we call oxoacids. These are simply acids which are made from polyions containing oxygen. And non-oxo acids are the opposite of that, obviously. Acid plus polyion without oxygen. about everything in the list except the cations and cyanide or oxoacids in this context. So here, get your polyion list. Try to draw out. Okay. NO2 and I'll put it over here. NO3 minus. One is a nitrite. This was nitrate. Well, the ending dictates how you define that. Now, if I'm going to make this into an acid, all I need is one hydrogen, HNO2, or here, still only one hydrogen, because I'm neutralizing the NO3, -1. So once I see this HNO2, I know that is a nitrate with a hydrogen. It becomes an acid, assuming AQ, or AQ, either way. It becomes nitrous, and you tag it with acid. And ATE becomes IC, acid. So that kind of shows you the progression of logic in the nomenclature here. So if we could go on to others, SO3, 2 minus, SO4, 2 minus. Okay, this is a sulfite. This is a sulfate. That looked like a 3 anyway. Right there. Of course, you would have to have 2 hydrogens on each one of these to turn it into an acid right here. Okay, because you'd have 2 negatives, and that would make that sulfurous acid, and this is sulfuric acid. See how the ATE drops to IC and so forth, like that. So this is common all the way through, and these are, of course, oxo acids. Here, right there. One that's non-oxo acid is the cyanide. IDE ending, like that. And so this, instead of an ITE, it's cyanate, or the cyanate ion. So it's got an ATE ending, so that would become one hydrogen hanging on there to neutralize the one negative, and so that'd be cyanic acid. So this is one of those non-oxo acids, but it is real, and it'll kill you real fast. I've never heard of it. Okay, so we could go down through all of these and make acids out of them just by hanging hydrogen. This is the one we've seen. This is sulfurous acid. This is a chromate, so it'd be chromic acid. Oxalic acid. Acetate becomes acetic acid. ACE, sorry. Like that. Carbonate, carbonic acid. Permanganate, permanganic acid. ClO3 chlorate chlorous acid. Chloric acid, I'm sorry. Here, the perchlorate is a ClO4 minus 1 right there. And that one is a perchloric acid. Now these things, there's some logic in here, and I'm going to show you that it's called an analogous series. I'll get there in a minute. Here's the HCN hypochlorites. This is hypochlorous acid. See, the ITE ending goes to OUS, so this has become hypo, LOROUS acid. It's one of the main ingredients in bleach and so forth like that. Bicarbonate, well, of course, that's HCO3 minus. It is an acid in itself because it has an ion of hydrogen on it, but it is not named as an acid. It's simply named as a bicarbonate, baking soda. Okay. Thiosulfuric acid, nitrate, nitric acid, sulfate, sulfuric acid, phosphoric acid, that's one. And hydroxide, that's from a base, so that's your OH group here. Usually your hydroxide, sodium hydroxide, blah, blah, hydroxide, whatever, like that. So there's some examples of taking the polyion and converting it over to an acid. When we're talking about analogous series, we're talking about a common element in a group of polyions. For example, in the halogens, there exists a ClO, ClO2, and all of them are the same oxidation state, minus, like that. But there's also, the only difference between these and what I'm about to write is the halogen. So you can, say if you have a chloride, then you can go to bromide, and the same combination applies like that, and iodide does the same thing. Okay. Now, in naming these, if we, of course, put a hydrogen on these, they're either OUS or ic acids to get to the acid form of this. So I'll take this one, but you change it systematically to the bromide or iodide. So I'm going to name this set, and you'll see how the next set is easily named from the systematic listing. So this is called hypochlorous acid, right there. Well, then that would be hypobromous acid and hypoiodous acid. See that? That's called analogous series, a similar series. And then you have chlorous acid, and it takes the polyion with the ClO2 this time, right here. And then when you get to the chlorate, ClO3 is a chlorate, it comes chloric acid. And then when you get to the last one, it's perchloric. And as a matter of fact, that's also a strong acid. There are only 6 strong acids. So how do you tell if it's a weak acid? It ain't a member of the strong 6. That's how you tell. So I mean, it's really easy. Anyway, we'll get to that in the next chapter more than this one. But now you can change the halogen and name in the same sequence of naming. Hypobromous acid, hypobromous acid, bromic acid, and perbromic acid. And all you do is change the Br in here from chloride to bromide. Iodous acid, hypoiodous acid, iodous acid, iodoic acid, periodic acid. Those all are commonly used chemicals in the industry. And so it's systematic. As long as you understand that, well, I can just change the halogen. Everything else stays the same in terms of the nomenclature and the combination of elements in there. Now, the source of the hypos and the chloruses, and the chlorics and the perchlorics, and those are based upon what the oxidation states of these elements are in that compound. Now, here's something you need to understand. As I presented the concept of oxidation state, charges on elements, I first started with those that are on the periodic chart. Well, they aren't combined with anything. So I say you've got, say, sulfur. Okay, how did we get to the octet? Okay, add 2, so it comes up with a -2. Well, that's the by itself element. Or chlorides in here. Chlorine, if you look on the periodic chart, is 7 outer shell electrons. Well, it has a space for 1 more electron, right? And so all the halides are -1. I think everybody kind of understands. But, big but, if you put that element in a compound, it may not be corresponding to that periodic chart. So you got to mentally understand that. Like in this, in the chlorides, this is actually a +7 oxidation state. This is a +5 oxidation state, +3 oxidation, and a +1 oxidation state. Believe it or not. I'll show you how to get to that.